Alright, so this is the tutorial on how to draw Newman projections. And so we're going to look at drawing these Newman projections. We're going to start off by the simplest case, looking at ethane. So why do we draw Newman projections? Well, they offer us a different viewpoint on looking at the bonds and looking at what things are interacting with each other. So we can have this viewpoint for this rotational analysis. So let's look at an example. Let's start with ethane. So if I just draw ethane, and I just draw it as, say, CH3 bonded to CH3. So there you go, there's ethane. And if I look at this doesn't really tell me much. It doesn't show me where the bonds are. It doesn't show me where the each individual CH bond is. Is it overlapping with another CH bond? Because remember, everything is in 3D. So if I come over here and I want to draw something like CH3 in a tetrahedral geometry, so I can come and start putting these H's on and do this in sort of a 3D form, and then we connect these to another one here. I'll put another H there, and then we have this H going back and then this one going forward. You can kind of see that, okay, we've got this 3D structure. So we need to figure out kind of what's kind of bumping into each other. Are they all equal? Does everything look the same? Right? And remember that in this, all carbons are now sp3 hybridized. Right? So if they're sp3 hybridized, that means everything is tetrahedral. So if I want to look at this, you can see kind of by the way that I have it drawn, I can make this look a little different by maybe drawing what we call a sawhorse representation. Right, so you can see where the two H's there, I have two of them coming down, one going back, one coming out, and one sticking up. We can make it look like a sawhorse with these two guys coming down. So I'll just draw something that looks like this. Put the H there and the H here, and I'm going to connect it to the back carbon, and then I'm going to draw or fill in the rest of the bonds. And what you see there is sort of the representation that we're showing. So you can see we have this kind of sawhorse looking structure. Okay, so now what we want to do is put your eye directly on the carbon that's in front. Now if I do that, that means that I really can't see the carbon that's behind me. It's kind of like a lunar eclipse, right? The moon comes in between the sun and the earth, and so you can't see the sun, right? So that's kind of like the back carbon. So if you can imagine my eye right here, what I'm trying to draw, here we go. Got some nice eyelashes there. And here's our carbon. We're looking down the center of this carbon, and if I do that and I align it directly, that means that I can't see the carbon behind me. So I can draw a representation of what it might look like by drawing this sort of peace sign looking deal, where this represents the carbon that is in front, and then the back carbon is going to be represented by a circle, because remember, I can't see the back carbon because it's totally eclipsed by the front carbon. So now if that's the case, then I'm just going to fill in all of the bonds. So I have hydrogens there on the front. We have 3 hydrogens. And then I can see that the back carbon right there, I have one sticking up, this guy. And so it's directly behind what the first carbon, the first hydrogen there is. So I'm going to put an H right there. And then if I put another H here, and another H there, that's exactly what it looks like, right? Because I'm looking directly down the bond line. Okay, so now what we can see is that basically we have this thing called a dihedral angle, and that's this area that's highlighted in green, right? And so what you can see is that this dihedral angle is 0 because they're both aligning on top of each other. Now let's redraw our Newman projection. So I'm going to draw this again, and let's just fill in all of our hydrogens. And so here we have all of these, they're totally overlapping each other. Now, what I can do is I can take this and we can rotate it. So if I rotate this about 60 degrees, then what I'm going to notice is that they're no longer going to be overlapping. So I'll have one that's in between each bond. So here's our hydrogens again, putting everything in now. And what you can see is that they're no longer overlapping. They're in between. And because of the fact that they're not overlapping, they are lower in energy because now we don't have the two electron clouds bumping into each other. Remember, a negative and a negative are going to repel. And so this gives us the names of the two different types of conformations. And this would be called different conformers because they're different conformations. We have the eclipsed, where they're totally overlapping, and we have the staggered, where they're in between each other or they're staggered. Now let's look at butane. And what we're going to do is we're going to look down the C2 to C3 bond of butane. So I'm going to draw this Newman projection first. I'm going to start, and what I can see is I have a CH3 coming off of the first carbon. That's that guy right there. And then I notice that the carbon that I have in the center, I have two hydrogens that are coming off of it, so I'm going to draw a hydrogen right there on each side. So I've taken care of C2 now. And now I need to go to the next one that's behind it, and what I notice is that I have another methyl group, right, coming off the end there. So there's a CH3. And then I have two hydrogens again that are on the C3 carbon. Now if we take this guy and we rotate it 60 degrees, then what we can see is here we now have a different structure or a different conformer. And so you can see I've moved now this CH3 that was directly eclipsed, I've moved it over 1. And so now it's no longer eclipsed, it's kind of in between the two. So it's in between the CH3 and the H. And then if I rotate it again, I end up with another conformer that also shows me something else that's eclipsed. So I have a CH3 here, and then again I'm going to have the rest of the bond. So we're going to hold the one carbon, carbon 2, we're going to hold that still the whole time while we rotate everything. And there you go, we have another CH3 and the hydrogens. And again, you can see that all of these are also eclipsed. But there are different energies here, so we need to pay attention. Now, if I rotate it one more time, what I can see is that now I have the two CH3 groups. They are completely opposite from each other. And so they're as far apart as possible. So now we have some different names that we can call this. because we have some extra groups. So we have the eclipsed, of course. And we have these two CH3 groups that they are basically eclipsed behind each other, and the CH3 is interacting with the CH3. So you can imagine that this may be higher in energy. Now I have this one where they're staggered, but we need another name because we need something else to define it. And so we're going to call it gauche. And if I rotate it one more time, I can see that I have something that's eclipsed again. And then finally I get to the last one where it's lower in energy, where the CH3s are far apart. That would be what we call anti. Now we can add up all of the energies that are associated with all of these different bonds. And so if we look at a chart, so here's a chart that shows you the different energies that are involved. And so if I draw a Newman projection, and here I'm going to draw the eclipsed version where I have two CH3s that are acting right against each other. And I have my two hydrogens there. Everything's eclipsed. Everything's overlapping here in this case. We rotate it again. We're going to rotate 60 degrees. And now I have my gauche conformer, where I still have these two CH3s, even though they're apart, farther apart from the eclipsed version, but they're still close enough to interact. So there is some level of energy there. And then if I rotate one more time, what I can see is that I now have this eclipsed interaction between the CH3 and the hydrogen that's there. And if I draw it again by rotating one more time, I can see that now we have the anti-conformation. So what we can do is we can actually look at these different energy values, and we can see that in this first conformation we have one CH3 to CH3 eclipsed interaction. So I can take this and I can look at the chart, and I can see that a CH3 to CH3 eclipsed costs me 11 kilojoules per mole. Now I have also two H to H eclipse interactions, and so these cost me 4 kilojoules per mole individually. So we can add all of this up, and this gives me a total energy cost of this conformer of 19 kilojoules per mole. Now we can separate this and look at the next one. So what I can see is I have a CH3 and a CH3. They're not eclipsed, but they're gauche, and so they're not anti. So that means that there is some energy associated with them. And so I can see that this conformer, if I look at the chart, I can tell that the only energy value that we have is 3.8, and so this conformer has an energy value of 3.8 kilojoules per mole. Then now I want to look at this one. So now the one that we're eclipsed again by rotating another 60 degrees, what we can see is that I have a CH3 to H, and I have two of those now, and then I have a H to H eclipsed also. So now I'm going to add up all of those, and so what I can see is CH3 to H eclipsed. That's going to give me 6 kilojoules per mole plus 6 kilojoules per mole, and then finally the H to H eclipsed. That's going to give me another 4 kilojoules per mole. So I can see I have a total of 16 kilojoules per mole. And then finally, when I get to the anti-conformation, what I note is that I have 0 energy interactions there. And so I have basically minimal energy at this point. So there you go. That's how you can look at Newman conformations to show you how much energy you have. And you're all done.